We all love our ClojureScript, but it gets even better when you combine it with the vast amount of JavaScript libraries out there. There's more than one way to do that, and because of the way ClojureScript compilation works, there are a few snags to watch out for. You're going to see quite some JavaScript Interop forms in this episode. If you're still a bit fuzzy on those, then I recommend first watching the episode on JavaScript Interop. I've created a minimal ClojureScript project that demonstrates all the ways in which you can include a JavaScript library from ClojureScript. It's on GitHub under lambda island/thirdparty.js. I use a separate branch for each thing I'm demonstrating, so you can easily check them out. The project setup is fairly typical. Here's project.clj for lining in. I included ClojureScript with the latest version, and then the line CLJS build plugin so I can build my ClojureScript. I'm not using Figwheel on this project, I'm just keeping it simple. And then there are two builds. One does not use any optimizations, this is the development build, and then there's a production build which has advanced optimizations. I've created a single namespace, thirdpartyjs.core, and it just contains one line of code so we can see that everything's working. And then finally there's an index.html which loads the compiled ClojureScript. So far so good. The main advice I want to give you is to use CLJSJS, found at cljsjs.github.io. If there's nothing else you take home from this episode, if you stop watching now, just remember this. Look for your library that you want to use on CLJSJS and follow the instructions there. CLJSJS is a community effort to package up JavaScript libraries so they're easy to consume from ClojureScript. A few hundred libraries are already packaged up, and more are being added all the time. Using a library like this only takes 3 steps. First, find the library on cljs.github.io, and then copy the dependency vector into your lining and or boot configuration. Now look at the usage instructions to find the provided name of the package, also known as its synthetic namespace. By requiring this into our own namespace, we make sure that this package gets loaded. And here's some example code that then uses D3. Now this isn't an episode on D3, so I'm not going to type this all in and explain it line by line. It's all in the GitHub repo if you do want to play with it. What it does is draw the outline of an iceberg, which looks like this. Now what you want to note about this code is that we included the cljsjs.d3 namespace, but there's actually nothing in that namespace. When we access D3, we do it through a JavaScript global, the same way you would do in JavaScript. The cljsjs.d3 namespace is called a synthetic namespace. It doesn't really exist. It's only used to signal that this code uses D3, so it will be loaded. Now let's start with doing a development build, so that's without any optimizations. The command is line cljs build once def. This goes relatively fast. Open index.html in your browser and you should see the outline of the iceberg. Now let's try a production build. First do line clean to remove any build artifacts from the development build, and then line cljs build once prod. This takes a little longer because it's optimizing and compressing your code. When it's done, refresh the browser, and the iceberg should still render just as before. Now suppose that for whatever reason, CLJSJS is not an option. Then what do? What I'm going to show you here is how to take this link from a popular CDN, content distribution network, and just put it in your index.html so D3 gets loaded from there. Now the D3 global will still be made available as before, so our code doesn't really change, but we no longer need to require this synthetic namespace, so this require can go. I'll also take out this CLJSJS dependency just to make sure that it doesn't get in the way. Now do a development build and reload your browser again. Seems that this simplest thing that could possibly work actually worked. It almost seems too easy. And well, maybe it is. Let's try a production build instead. Reload the browser. Oops, looks like we broke something. Peek under the cover and you'll see an error message like this one in the console. Type error, d3.select.append.va is not a function. d3.select.append, that still looks good, but then it tries to call this VA method. That's not in our code. Where does this gibberish come from? Let's have a look at the compiled file, thirdpartyjs.js. You can open it in your browser, or I'm just going to open it in my editor here. Now, if you scroll down here, there's a lot of stuff. This is basically everything from ClojureScript, the data structures, the main functions, all packed together and optimized. And then all the way at the bottom, we find the bit that relates to our code. So we can recognize this here, d3 select append, some stuff is still recognizable, but then a lot of function names have been renamed. So how did our code end up like this? Well, the ClojureScript compiler makes use of the Google Clojure compiler. That's Clojure with an S, not with a J. This is a powerful optimizing JavaScript to JavaScript compiler, which is used heavily by Google for building things like Gmail or Maps or Docs. One of the main goals of the Clojure compiler is to reduce loading time by packing all the JavaScript together in a single file, and then making it as small as possible. It has a few ways of making the code smaller, including renaming functions to something shorter. In this case, it has renamed every occurrence of error with VA. Now when it does that all over the codebase, then that's not a problem, because the end result of running the code is still exactly the same. But we loaded D3 separately, and so Google Clojure hasn't been able to do anything with the D3 code. So we're calling a function now that no longer exists, leading the browser to divulge this universally acknowledged, inalienable truth: undefined is not a function. One way around this is to simply not use advanced optimizations. With whitespace, all the code gets packed together, but nothing gets renamed. With simple, only local variables get renamed, so this is always safe. If squeezing the last byte out isn't vital to what you're doing, then maybe whitespace or simple optimizations are good enough. These advanced optimizations are nice though. Can we have our cake and optimize it too? Google Clojure has its own module and dependency tracking system, a bit like CommonJS or AMD. If D3 was a library written for Google Clojure, then we could just add it to our build, and it would be optimized with the rest of the code. That's not the case though, but let's have a look anyway what such a module would look like. Here's a padding module that implements a left pad and a right pad function. The Google.provide clause declares the namespace that this module defines. Google.provide will create a JavaScript object with that name, so we can assign properties onto it. Any function we want to make publicly available, like left pad or right pad, must be added to this object. Make padding is just an internal helper, so we don't need to add that one. With Google.require, we can include another library, in this case Google.string, since we're using the Google.string.repeat function. Notice the name I used in Google.provide. It looks just like a ClojureScript namespace. That's because, for our purposes at least, it is. To save this file, use the same naming conventions as you would in ClojureScript, except that now instead of a CLJS, it has a JS extension. So namespace segments become directories, and the last segment becomes the file name. Now in ClojureScript, we can require this just like a regular namespace. Refer won't work, but as does, so you can give it a more convenient alias. Now, to just quickly show that this is working, I'll enable console print, and then call leftpad and print out the result into the console. So it seems like this works, both with the development build and with the production build. Let's have a look under the covers, how they actually differ. This is the HTML that we sent to the browser. It's pretty minimal. There's just one JS file that we load. Now the inspector in your browser tells a very different story. Here's the one file that we started with, but it seems that one added at least another dozen script tags. So where do all of those come from? If you look at thirdpartyjs.js, you'll see that it doesn't contain any application code. All it does is inject some tags to do the actual loading. 3 of these are important for us. Base.js contains supporting code for Google Clojure's module system. It's here that Google.provide and Google.require are defined, so code can be loaded dynamically, on the fly. CLJSJS is a generated file containing a list of calls to Google.addDependency. Together they form the dependency graph for our application, specifying the dependencies between namespaces and the files they are defined in. Once all of that is done, a call to google.require will load the third-party JS.core namespace. All of the necessary dependencies need to be loaded first. This core namespace depends on padding and also uses ClojureScript built-in functions, which are defined in CLJS.core. So in turn, CLJS.core depends on stuff from the Google Clojure library. So that's what all of this is. Now when these are loaded, then CLJS.core can be loaded, then we load padding, and then with those there, we can load the final core namespace. I hope you managed to follow all of that. The reason I'm showing you all this is to drive home the point that when optimizations are disabled, Google Clojure forms a dynamic module system, where each namespace forms its own file, and namespaces can be loaded at runtime. When we go to the other end of the optimization spectrum, skipping whitespace or simple optimizations and moving straight to advanced, we get a very different picture. I now did a production build, so with advanced optimizations. It's still using the same HTML, containing a single script tag, but if you look at the inspector, it's no longer loading any extra files like it did before, so it must be that our whole application has now been packed into this one file. Now if you look at it, you'll see that it's highly optimized code, not meant for human consumption. But with some effort, you can still find left pad in there, except now it looks like this. Here I've put the generated code and the original next to each other so you can compare them. Several things are remarkable about this bit of generated code. The make padding function is gone. It has been inlined into left pad. Namespaces are gone, instead every individual function has just gotten a unique short name, flattening the hierarchy. And what happened to right pad? Well, it's simply gone. Google Clojure figured out we weren't using it and simply ripped it out. The same happens for ClojureScript core or library functions. If you don't use it, you don't pay for it. That's one of the superpowers of ClojureScript. The takeaway from all this is that what was essentially a system for loading dependencies at runtime now becomes a tool for analyzing and optimizing code, and given the magic it does, it's also easy to see how things can go wrong. Back to D3. We understand now what went wrong. By having D3 outside of our build, the compiler doesn't know what functions it's defining, and so it can't take that into account. We need to tell the compiler that it should leave certain function names alone, because they're defined elsewhere. This is done through an externs file, a JavaScript file that doesn't contain any implementation code, but instead just defines declarations for all the identifiers that should be left alone. Here's a small externs file with declarations for all the bits of D3 that we're actually using. Save that as d3externs.js, and then add it to the ClojureScript compiler configuration under externs. Now we can do an advanced compilation without breaking the app. In this case, we're only using a handful of functions, but for a real-world application, you really don't want to be writing these externs manually. Luckily, there are tools to generate them for you, like this online externs generator by Michael McClellan. Just put in a link to the D3 source file, choose which top-level variable you'll be referencing, in our case that's D3, and then click on extern. Copy the result over to your extern file and you're done. Or at least, mostly done. Occasionally it might not detect all the necessary externs, and you need to add a few yourself. Doesn't sound like fun? That's why we have CLJSJS. CLJSJS packages already have the necessary externs included, so you don't have to worry about them. If you have choice in the matter, then always use CLJSJS, but I already told you that. So far we're still loading D3 separately from a CDN by adding an extra script tag. That means doing an extra network request, and if we get more dependencies, that is going to get costly. It would be better if we could compile D3 together with the rest of our code into a single artifact. Let's first pull D3 down so we can use it locally. To get a JavaScript file into the build that isn't the Google Clojure module, you need to use the foreign libs option in the compiler configuration. Foreign libs takes a vector of maps, one map for each file you want to include. First point it at the right file, and then use provides to give it a synthetic namespace. Provides takes a vector, but normally you just put a single string in there. All this will accomplish is including the D3 source as is in the final output. It just concatenates the files together. It won't analyze it or do smart optimizations, so we still need the externs file to make sure our own code stays compatible after optimizations. Now, just like with CLJSJS, we need to require this namespace, otherwise D3 will not be included in the build. Afterwards, we can reference D3 just like any JavaScript global. This final approach of using foreign libs with externs is usually the recommended one. It doesn't allow Google Clojure to optimize a third-party library, but for many libraries that will probably never be the case, given there are some very specific requirements in how the code should be written. This is also the approach taken for most CLJSJS packages, although some libraries are actually compatible with Google Clojure and are packaged up as such. What I haven't told you yet is that Google Clojure compiler ships with the ability to load other module formats, like CommonJS or EMD or ES6. It's still a bit of an experimental feature, I definitely had some mixed results trying this out, but I'll show you anyway, because it's a pretty cool feature, and because it lets you imagine what might be possible in the future. To show you how that works, I've changed padding.js to use ES6 import and export statements. With import, I'm pulling in the gook string repeat function. This gook colon prefix is needed here to show that this is a Google Clojure namespace that we're loading from, and not another ES6 file. You can also use it to import functions defining ClojureScript namespaces, which I think is pretty wild. Finally, it exports left pad and right pad, the two public functions of this padding namespace. To include an ES6 module, also added two foreign libs. We specify the file name and the provided namespace just like before, but now also add an extra option, module type. Adding this module type makes a pretty big difference. Where before the foreign library would naively be concatenated with the rest, now it becomes a first-class part of the build, taking part in dependency resolution and getting the full load of optimizations. This also means that we no longer need the externs. The application code hasn't changed. We still just require the namespace and then call the left pad function. I don't know about you, but I think that's pretty cool. That's it. You now know all there is to know about using JavaScript libraries from ClojureScript. Most of the time, CLJSJS will be all you need, but sometimes it won't be, and with this stuff under your belt, you should have all the tools available to figure out whatever challenge comes your way. Thank you for watching Lambda Island.